Congratulations! You've almost made it through Module 1 in ABS 470. This is the last lecture for the week. Professor Jared here, and today we're going to be focusing on mammalian dentition. So I think you're going to find this lecture extremely helpful for your Module 1 assignment on mammal dentition and skull structure. And I can also assure you that you're going to have dental formulae on your first assessment at the end of next week. So this is going to help you with those questions on your next test. In this video lecture, I'm going to cover the second part of characteristics of modern mammals, and that's entitled Dentition. So you may recognize this skull from illustrations in our last lecture when we touched on the Pleistocene megafauna. This, of course, is the saber-toothed cat, Smilodon, and its 8-inch canines. We've thus far established that mammals are essentially eating machines with high metabolic rates that are necessary for endothermy. Although all mammals are going to start out their lives solely drinking milk, upon weaning, they're going to enter into one of numerous adaptive feeding modes. And we're going to take a deep dive into modes of feeding in Module 6, Week 6. But for now, recognize what I mean by an adaptive feeding mode is carnivory, herbivory, the frugivores, the insectivores, and of course the generalist omnivores, like this species right here that's capable of subsisting on an incredible range of foods, from cultures in the Arctic that thrive on marine mammals to entire cultures that are built on rice in Southeast Asia, to the San Bushmen in the Kalahari Desert running down antelope. So these modes of feeding are going to be reflected in the animal's specialized teeth. So those teeth are going to tell us about their mode of feeding as well as their trophic level in the food web. With respect to tooth anatomy, what I want you to recognize is that the occlusal surface here, the chewing surface, is covered with this very hard crystallized mineral called enamel. Enamel is not composed of cells, it's composed of calcium phosphate. It's an incredibly durable structure. It's actually harder than any other vertebrate tissue. And then below the enamel, we have the living dentine. That makes up most of the tooth. Okay, the dentine is fed by blood vessels here in this pulp cavity. And then I certainly don't have to tell anybody that's ever had a toothache that the pulp is innervated. You can see the nerve here coming through the root canal. It's these yellow tracks here. The incisors of rodents are deemed open-rooted because dentine growth is continual. And what's going to happen is you're going to have differential rates of wear between the very hard enamel here on the anterior surface and the dentine right here. So the dentine is going to wear away faster, and it's going to create this sharp, continually sharp chisel-like edge that is just perfect for gnawing on tree nuts and seeds and even wood in the case of the beaver and the woodchuck. Very quickly, I want to show you this small beaver skull that I have. And it's not a great specimen. It's a little broken, and it's actually missing an incisor. But you can see that one bright orange incisor. So this is how you're going to recognize rodents, be it a naked mole rat or a Norway rat, or in this case, a small beaver. Rodents are recognizable by their orange incisors. That orange is the enamel. Okay, so that's the incredibly durable substance. And then if we flip it up and over here, you can see the dentine, and you can see how this thing has a really nice sharp edge to it, a nice beveled edge, almost like a knife. So the rodent incisors, the open-rooted teeth. As most teeth mature, the root canal gradually closes off and the pulp cavity with the blood vessels is sealed. These are now deemed close-rooted teeth. As the teeth are now no longer growing, they begin to wear away with use. Now, there's considerable individual variation depending upon diet, but generally speaking, animals such as this white-tailed deer can be aged by carefully examining tooth wear. So, for example, by 1.5 years of age, you can see here this third premolar of the white-tailed deer is already showing some heavy wear. Also, this is tooth 6. It has just erupted. By 3.5 years of age, the dentine is really showing. The dentine is the dark part. It's now wider in some places than the enamel, which is the white part. Okay. By 5.5 years of age, the dentine showing is now twice as wide as that hard white enamel. And by 8.5 years, numerous enamel ridges are completely worn away, and these molars are just totally dished out. Okay, so compare those dished out molars to this juvenile elk. So this is a yearling elk, the lower jawbone, and I want you to see how sharp those enamel ridges are on both the molars and the premolars. Okay, so this is a young animal showing very little tooth wear at this point, a juvenile elk. That said, the most accurate method for aging mammals is to look at layers of cementum, which is a modified bony material that is laid down annually around the root of the tooth like rings on a tree. So you can see these layers, these annual layers of cementum. The leader in the field for cementum annuli aging analysis is Gary Matson out of Missoula, Montana. So I worked with Gary about 20 years ago now when we were trying to understand the age distribution of cow elk in the Blackfoot Valley in Montana. So we asked successful hunters to send in the first premolar of their cows. Canine is actually better for this analysis, but as any hunter will tell you, they don't want to part with those canines, the ivories, as they call them. They keep their ivories. Numerous lineages of mammals have independently lost their teeth. These are called the edentate mammals, the toothless mammals. So important, this is a secondarily derived characteristic, as evidenced by the observation that many embryos of these species will begin to develop teeth only to have them reabsorbed later on during development. Further, the edentate condition is not homologous. It's not shared by a common ancestor of these different lineages. Rather, all of these lineages have independently converged on this anatomy. Those lineages include the monotremes, the spiny echidna here, the order Pilosa, this anteater right here, the pangolins, which is the order Pholidota, So these species are all primarily gobbling up ants and termites. And then lastly, we have the Mysticetes, the baleen whales, the filter-feeding whales, like you see down here on the bottom left. So they have this highly specialized structure called a baleen, which is rooted in the upper jaw. And the function of the baleen is to strain out copious amounts of plankton, like krill. There are several species of mammals that do exhibit homodont dentition. That is to say that their teeth do not vary in form or function. They're all essentially shaped and sized the same. So those lineages include the Odontocetes, that is the toothed whales, like this bottle-nosed dolphin here on the right, as well as the armadillos. The armadillos are in the order Cingulata. That said, the majority of mammals exhibit heterodont dentition. That is to say, different types of teeth that vary in their morphology, their shape, as well as their jobs. So these teeth include the incisors at the anterior of the upper and lower jaw, denoted in blue on this image of a wolf skull, the single pair of canines in green, the premolars, which are in purple on this picture. And then lastly, we have the molars in light blue. So let's take a moment and focus on each of those types of teeth. Incisors typically have a single root and are most often used to snip in the grazers and the browsers, to tear in the carnivores, and then to gnaw in the rodents, like this capybara here, which is the largest rodent in the world, gnawing incisors in the rodents and the lagomorphs, the rabbits and the hares. That said, like so many structures in nature, incisors can be highly modified to do specialized tasks. So consider the incisors of the vampire bat, which are adapted for piercing flesh so that it can lap up the blood. The incisors, those are incisors of elephants, which are used for digging as well as stripping bark off of trees. And then lastly, the incisor here on the narwhal, which is most likely used to attract mates and to compete with rivals in sexual selection. Please note that there is never more than one pair of canines in the upper and lower jaw on any modern mammal. So like most of the incisors, the canines are unicuspid. They just have one point, one protrusion. Incisors are single-rooted. They're especially pronounced in the carnivora, like you can clearly see here in this tiger, for piercing and tearing prey. Let's see, canines comprise the tusks in walruses and the Suidae, the pig family. Surprisingly, we even see elongated canines in some deer, like the musk deer of Southeast Asia, as well as the Chinese water deer in the Yangtze Basin and Korea. Moving on to the first type of cheek teeth, the premolars. The premolars are immediately posterior of the canines. So admittedly, it can be kind of tricky distinguishing between the premolars and the molars. Here you can see in the horse, they look a lot alike. So in general, the premolars are going to be smaller than the molars, and they most often have two roots, whereas molars most often are going to have three. However, the best defining characteristic for distinguishing between premolars and molars is that the premolars are going to have deciduous counterparts. There are milk teeth of the premolars. So those baby teeth premolars are going to come in and then be replaced by adult premolars. Whereas the molars, there are no deciduous counterparts. And finally, we have the multicuspid molars, which again, unlike the premolars, have no deciduous counterparts. Premolars and molars are collectively deemed the cheek teeth or the molariform teeth. The function of these large teeth is for grinding food. This grinding, this mechanical digestion is very important to maximize nutrient absorption from foods. Of note here, crown height is going to vary considerably in the mammals. Herbivores, which consume highly abrasive forage that contains lots of silica, so it's really hard on the teeth, like this horse, they are going to have very high crowns. They're called hypsodont. So hypsodont means high crowned. And you can see that those high crowns are deeply embedded in the horse's jaw. Over here in the omnivores, the crown is considerably smaller. This is referred to as brachiodont dentition. Further, the cusp patterns are quite variable on the occlusal or the chewing surfaces of cheek teeth. So brachiodont, remember brachiodont has the low crown. Brachiodont cheek teeth are most often bunodont, which means they have rounded cusps for crushing and grinding, like we see in the monkeys and the pigs. Alternatively, the cusp may form this continuous ridge or loaf, such as occurs in elephants in a pattern termed lophodont. And then finally, if the loafs are isolated and crescent-shaped, as in deer, like this elk or wapiti, we deem it selenodont. And I'm going to show you some skulls here with all of these cusp patterns in just a moment. The carnassial teeth are highly specialized teeth in the order Carnivora. They're the last upper premolar and the first lower molar. And together those carnassial teeth are used for shearing meat, like you see here in this African lion. So a quick look at the carnassial teeth in a number of carnivore families. These are the carnassials on an ursid, a bear. B is the felids, the cat family, like this lion. C is the canines, of course dogs, wolves, coyotes. And then lastly on the bottom we have the mustelid family. This is the weasel family with wolverine, badgers, and otters. Another term you should be familiar with, the diastema. The diastema is a gap in the tooth row between the incisors and the molars, the cheek teeth, as exhibited by this white-tailed deer, as well as in the rodents, like this gray squirrel here. Again, this is the diastema, this gap in the tooth row. Important to note, these teeth have been lost over evolutionary time, so the rodents have no canines, they've lost those. Most mammals are diphyodont, meaning they have two sets of teeth during their lifetime. Di, of course, means two. They have their deciduous or milk teeth, as well as their permanent adult teeth. The exception is shrews. Shrews only have adult teeth, but that said, they do in fact have deciduous teeth. They're just reabsorbed during fetal development. So here we can see an x-ray of a human, and you can see these permanent teeth pushing out the milk teeth, the deciduous teeth. There's a canine here and a premolar. Interestingly, in the elephants and the manatees, the adult teeth are going to move from the posterior of the jaw. They're going to move horizontally, and the adult teeth are going to replace the cheek teeth that wear away and fall out. Okay, so let's take a few minutes and let me walk you through dental formulae. A dental formula is just a shorthand description of the total number and position of the teeth. Some important points to start. Number one, dental formulae are always given in this order. Incisors first, then canines, then premolars, and finally molars. They're always given from front to back, from anterior to posterior. Number two, dental formula are only given for one side of the mouth, okay? Because mammals are bilaterally symmetric. So what's going on this side of the mouth is going to be the exact same number that's going on this side of the mouth. And then number three, the upper jaw is always on top or to the left of the backslash, and the lower jaw is always beneath. Okay, so here we have a wolf, Canis lupus, and you can see 3 incisors on top, 3 incisors down below, 3 canines, 1 and 1. There's always just one pair of canines if they're there. Then we have 4, 1, 2, 3, 4 premolars on top. 1, 2, 3, 4 premolars on bottom, 2 molars on top, and then 3 molars on the bottom. Okay, 1, 2 is there, and 3. Okay, so that's a total of 42 teeth on the wolf. All right, so I don't have a wolf, but I do have its close cousin, the coyote. Okay, coyotes have the same dental formula as wolves. They have 42 total teeth, same exact positioning. In fact, all canines do. They all have the same dental formula. So we're going to start with the upper jaw, and I'm going to try and get you a nice close look here. We are supposed to have 6 incisors across the front here, but we're actually missing 1. Okay, so if we have 6 total, we're only going to do one side. So one side means that we have 3 incisors. We just have the one canine, the large pointy canine. We have 1, 2, 3, 4 premolars. This rather large tooth is actually a premolar. And then I'm going to turn it just like this, and you can see that there are 1 and 2 molars. Okay, the lower jaw is going to vary slightly. So we are again going to have 3 incisors on the one side, the canine, and then we're going to have 1, 2, 3, 4 premolars, and then we actually have 3 molars, 1, 2, and 3. Hopefully you can see those. Okay, lastly, if I can get this jaw to articulate again, there we go. I want to show you the carnassial teeth. Okay, remember the carnassial teeth, that last premolar on the top. There we go. The last premolar on the top and the first molar on the bottom, right here and right here. And if you can just see that, it's got this shearing capacity, right? So it's going to allow it to just shear meat. And the carnivores have the carnassial teeth. Next up, we have a bobcat skull. And a bobcat skull is going to have a dental formula of 3 incisors on top, 3 incisors below, one canine on top and one canine below. And then it's going to have two premolars on top, 1, 2 premolars, 2 premolars on the bottom, and then it's got, and I know it's kind of hard to see, it's got one tiny little molar up top, and then it's got a molar down below. So the bobcat has a total of 28 total teeth. I want to show you those carnassial teeth again. Okay, that shearing action from the carnassial teeth. But most importantly, what I want to show you on this bobcat is I want you to check out the very short rostrum. The rostrum right here in the anterior part of the skull with the nasal cavity, as well as the very short lower jaw, at least relative to a black bear. Okay, so here's a black bear, and I'm going to try to get them both in the camera for you. Okay, so you can see that relative to a black bear, an omnivore, this highly carnivorous cat has a much shorter rostrum and lower jaw. Okay, this cat has a much greater bite force, pound for pound, than either the bear family, the ursids, or the canids. This is the most carnivorous of the carnivores. Why does it have such great bite force? Well, if you remember your unit on simple machines from way back probably in middle school, this lower jaw right here represents a third-class lever. A third-class lever has the fulcrum on the end, so the fulcrum is here where the lower jaw articulates with the skull. The effort is provided by the masseter muscle. The masseter muscle is going to go through the zygomatic arch and connect to the lower jaw. And then most importantly, the load. The load is the bite force. Okay? This cat has a very great bite force because the load is closer to the fulcrum than this black bear. This is also a third-class lever, okay, but here you can see that the length of the lever arm is considerably longer. Okay, so the lower jaw, a third-class lever, the shorter the jaw, the greater the bite force. That said, don't let this omnivore label fool you. We'll come back to this in Module 6, but one thing I learned 20 years ago now, putting radio collars on newborn calf elk, is that black bears, and especially grizzly bears, are very effective predators at hunting and killing neonatal elk, newborn calf elk. All right, I've got two more omnivores for you. First, I have a primate. I have a chimpanzee, and then I have a collared peccary, which you may know as the javelina. A couple of things I want to point out. Number one, on the javelina is brachiodont. Brachiodont. So what that means is it has low crown heights. The second thing that I want to point out is the occlusal surface of a brachiodont. Here is the lower jaw from the chimpanzee, and so this is what we call bunodont occlusal surfaces. So if you look really closely, you can see those rounded cusps on the cheek teeth. Contrast that with a zebra, and the zebra has hypsodont dentition, or high-crowned cheek teeth. Further, the zebra is going to have solenodont occlusal surfaces. So those are those crescent-shaped cusps, okay, that are not continuous. This is Solenodont dentition, a Solenodont cusp pattern. Finally, I wanted you to note these incisors for cropping grasses, the zebra. And just two more really quick, a couple more specimens I've collected over the years. First, I wanted to show you this Russian boar. And the reason why I wanted to show you this dude is because of these modified canines. So the canines are these gnarly tusks on the Russian boar. And then I've already shown you the beaver. You remember the beaver. It's a small beaver. It's got the orange enamel on the incisor, the dentine, which is going to wear away much more quickly, creating this beveled edge. But what I wanted to really show you was the diastema, that gap in the tooth row. All right, so I'd like to end with a little bit of practice for you. So I'm going to give you about 30 seconds. Grab your pens, grab your journals, your notebooks, and I want you to practice scrawling out the dental formula for the white-tailed deer. Notice that the teeth in the lower and the upper jaw are labeled with letters and numbers. So it should be pretty easy. So I'll give you just a few seconds on that. Drum roll. The answer is, on the top, we have no incisors, so a 0 goes on top. On the bottom, we have 3 incisors. We have no canine on top. On the bottom, we do have one tiny little canine there, labeled C1. On the top, we have 1, 2, 3 premolars, and 1, 2, 3 molars. On the bottom, 3 premolars and 3 molars. 3 premolars and 3 molars. So that's a total of 32 teeth. To get the total, of course, you're going to sum those and multiply by 2 because we're just doing one side of the jaw. Fear not. You are going to get some more practice with both skull identification and dental formulae on your assignment this week. So you're going to check out this beautiful website entitled Teeth in 4D. It's Dr. Evans' lab from Monash University, and it's got these amazing digital models that allow you to manipulate them in any direction that you want. They're in 4D because they're moving, so it's going to be really helpful for you in working on dental formulae. It's the next best thing to actually holding the skull in your hands. And as always, I'll end with references. I really hope you find these videos helpful. Please reach out if you have any questions, and take care. I'll see you next time.